Hey, what's going on, Chem 20s? Lucky day. I think this might be the last time you have to put up with these videos. Oh man. Okay. Today we want to talk about 7.3, which is solution stoichiometry. Now it's going to be really similar to gravimetric stoichiometry, except there's a few crucial differences just in the way that we treat kind of solids versus the way that we treat solutions. So what I need you to do is I need you to get out your data booklet, grab your calculator and whatever you write your notes on, and then let's go ahead and get started. So this is going to be 7.3 solution stoichiometry. Now, we've been talking a lot about gravimetric stoichiometry over the last few days, and I just kind of want to recap that a little bit. When we talk about solids, solids are really kind of defined by two things. Like the amount of a solid is really kind of defined by two things. It's defined by the mass and the molar mass. Because the mass is typically measured in grams, and the molar mass is going to be measured in grams per mole. And what we can do is we can use these two things in unit analysis. The grams can cancel out and we can get moles. So that's helpful for stoichiometry because the way we transfer from one thing to another is using moles and the molar ratio. So it's helpful to us to use grams and grams per mole because the grams can cancel out and we can get moles. Now we want to talk about solutions, so we better kind of switch our mindset to how we define solutions or the quantity of a chemical in a solution. So as far as solutions are concerned, they're still defined by two things, except in this case, instead of the mass and the molar mass, what it is, it's defined by the volume and the amount concentration or the molar concentration. I'm just going to say concentration. Now, we measure volume in like liters or milliliters or something. I'm going to say liters here. So we measure volume in liters, and we measure concentration, at least molar concentration, molarity, amount concentration. There's a bunch of different words for it, but we measure it in, and let's just double check our data booklet because that'll be helpful for us. So when we take a look at our data booklet, I want to remind you that this page exists. So this is page 3 or something in your data booklet. And in here, it defines a bunch of things, and it defines the units for those values. And kind of in here at the very end, we have amount concentration, and it's being measured in moles per liter. So that's important for us to know. I just wanted to remind you that that page exists. So moles per liter. Well, this is also helpful in stoichiometry. Remember, stoichiometry requires moles to convert into a different substance of moles. So we use that molar ratio in order to convert from one substance to another. Well, when you look at these, having the volume and having the concentration, liters and liters can cancel and we'll end up with moles. So it's a very analogous situation. If you have a solid or if you're being given a mass, you need a molar mass. Well, if you have a solution, you need a volume and a concentration. Now, the good thing about solution stoichiometry is that you basically have to be given both of these things. Whereas in a solid or in a mass or something, you had to go looking for the molar mass. You had to go into the data booklet, into the periodic table, and calculate the molar mass. This time, I have to give you, or we have to give you both of these things. So it's actually a lot easier than gravimetric stoichiometry is. But we'll see how that goes. We'll see how it goes in the next case. So let's go ahead and let's just kind of dive into an example. So this is going to be example number 1. Ammonia and phosphoric acid can react together to make ammonium hydrogen phosphate. I'm being told that this chemical reaction is important in the production of fertilizers. I wouldn't know. Oh, whatever. Doesn't matter. So ammonia and phosphoric acid can react together to make ammonium hydrogen phosphate. What volume of 14.8 mole per liter ammonia is needed to react with 1.00 kiloliters of 12.9 mole per liter phosphoric acid. I know that's a big question, and I apologize, but deal with it. So, I'll give you a second to write that down. Pause the video if you need a little bit of time to write that down, whatever. Ammonia and phosphoric acid can react together to make ammonium hydrogen phosphate. What volume of 14.8 mole per liter ammonia is needed to react with 1.00 kiloliters of 12.9 mole per liter phosphoric acid? I totally get that this is a lot of information to take in. But please remember, whenever we're talking about stoichiometry, we need to talk about things as a balanced chemical reaction first, because we need to know how to quantitatively relate the two chemicals involved using the molar ratio. And then we're going to put whatever pieces of information we know about these substances under them in the chemical reaction, and then we're going to do some unit analysis. Stoichiometry really, you kind of get used to the flow of stoichiometry after a little while, and you're still probably pretty new to this process. So let's go ahead and make a balanced chemical reaction. We know this is stoichiometry because it's talking about what volume of ammonia is required to react with phosphoric acid. So it's saying how much of this to react with this. That's stoichiometry, relating two substances together. So let's go ahead and write a balanced chemical reaction. Ammonia is going to react with phosphoric acid. So we're going to need to know what ammonia is. That's one of those substances that hopefully you would have memorized at the beginning of the semester. If not, you can use pages 4 and 5 in your data booklet. So let's go ahead and write down the formula for ammonia. Ammonia is NH3, and it's hinting that it's a solution, so it's aqueous, and it's going to react with phosphoric acid. Now, if you don't know what phosphoric acid is, that's totally fine. Remember, because you can use your data booklet to try and go to the table of acids and bases and look it up. So when we go to look up phosphoric acid, phosphoric acid here is H3PO4. So again, I just wanted to remind you that that also exists, that the table of acids and bases is a thing. So it's reacting with H3PO4. And it's going to make this substance, ammonium hydrogen phosphate. Ugh. Okay, I don't know if you remember what type of substance ammonium hydrogen phosphate is. So it's either an element, ionic, molecular, an acid, or a base, something like that. When I take a look at it, it starts with ammonium, and that's really important. I want you to kind of think about it for a second and figure out what type of substance is that. Starts with ammonium, so it's, yes, an ionic compound, absolutely. So ionic compounds always start with metals or they start with ammonium. That's the other thing that they can start with. So because this is an ionic compound, we kind of want to deal with the ion charges. We need to make a neutral compound using the ion charges. Well, ammonium, what the hell is ammonium? Well, we can go to our periodic table and we can try and figure out what ammonium is. Some people already know what ammonium is, and that's totally fine. It's all good. But here, ammonium is NH4 with a 1 positive charge. So it's NH4 and it's 1 plus. So I'm just going to say that's 1 plus. And then I want to know what hydrogen phosphate is. Well, if that's an ion, this has to be an ion as well. It's an ionic compound. So we'll take a look at our data booklet again for hydrogen phosphate. And I see, whoa, hydrogen phosphate is HPO4 with a 2 minus charge. So it's a 2 minus charge. So how many ammoniums and how many hydrogen phosphates would we need? Well, 1 plus and 2 minus, we need 2 ammoniums for every 1 hydrogen phosphate. So NH4, but we need 2 of them. So bracket 2, and then hydrogen phosphate is HPO4. And we're assuming it's going to be aqueous. Okay, no problem. So we go through this chemical reaction. It's not balanced yet. We've got to try and figure out, okay, why, how, what are we going to do about this? Let's take a look. This is obviously the most complicated thing in here. And I take a look and I say, okay, there's nitrogen at the beginning, and the only place nitrogen comes from is from the ammonia. There's 2 nitrogens, so I might as well toss a 2 in front of here. And then I notice, okay, there's 1 phosphorus, and there's 1 phosphorus, 4 oxygens, 4 oxygens. There's a total of 2 times 4 is 8, plus 1, so 9 hydrogens. I take a look here, there's 6, right? 2 times 3 is 6, and 3, that's 9. This thing's balanced. So all the hydrogens, the phosphoruses, the oxygens, the nitrogens are all balanced. So all we had to do was put a 2 in front of there. I know that can be complicated, but please don't really dwell on that thing right now. Hey, we got a balanced chemical reaction. That's awesome. Now what we want to do is we want to start putting our pieces of information below the substances they belong with. So any piece of information from the question, we're going to put it below who it belongs to. So it says, what volume of 14.8 mole per liter ammonia? So it's talking about ammonia, and it kind of says 2 things. It says what volume and 14.8 moles per liter. So it says I'm looking for volume in liters. We always try and put the unit that we're looking for. That's what unit analysis is all about, putting the unit that we're looking for. So you can either say liters or you could say milliliters, and we can deal with that a little bit later. And then it says 14.8 moles per liter ammonia. Okay, no problem. 14.8 moles per 1 liter. That's the way I like to write it, because that's the way we always write fractions as top and bottom in our unit analysis, but it's up to you. Okay, what volume good of 14.8 mole per liter ammonia, good, is needed to react with 1 kiloliter of 12.9 mole per liter phosphoric acid. So over here we have 1.00 kiloliter of 12.9 mole per 1 liter phosphoric acid. So I'm just taking those things and putting them under the phosphoric acid. Now, if you don't know what a kiloliter is, that's totally fine. It's like a kilometer, but just for liters. So it's 1,000 liters. That's what it is. Now, I want us to keep the kilo in there because when we do unit analysis, it's actually really easy to deal with prefixes. It really is truly easy to deal with prefixes when we're doing unit analysis. So just leave the kilo in there, and I'll show you how to deal with it in our unit analysis. Awesome. Okay, so we're going to be able to get moles in here. We're going to be able to get moles in here because liters and liters can cancel, liters and liters can cancel. So that's great. That's all we need over there. And then finally, we need to be able to convert between the two. And the only way we can convert between one substance and another substance is with the molar ratio. So it's unknown over given, 2 moles of NH3 over 1 mole of H3PO4. And that's all the information we need in order to do this unit analysis. So let's go ahead and start doing our unit analysis. We're looking for liters. We're looking for liters of our NH3. So let's go ahead and do our unit analysis. Well, where do we have liters of NH3? I have no idea, but I'm going to look under NH3 and I'm going to look for liters. Hey, I got liters right in the bottom of this thing. So I have liters of NH3. All I have to do is flip our concentration for the NH3. So 1 liter of NH3 for every 14.8 moles of NH3. So do I have the unit that I want on top? Yes. Now all I got to do is cancel out all the other units and then I'm good to go. How can I cancel? So I'm done with this unit, right? Done with that piece of information. How am I going to cancel moles of NH3? Well, I look under NH3. I've already used the moles, so I can't use it again. So I'm going to look for some other piece of information. Whoa, lo and behold, our unit, our molar ratio has moles of NH3 in it. So 2 moles of NH3 over 1 mole of H3PO4. So what did that do? That cancels moles of NH3 and moles of NH3. I like to cancel the word mole and NH3 all in one go because they cancel each other out. Oh, shucksy doodles. Now we got to cancel out moles of H3PO4. Well, I've already used this thing, so I can't use it again. So I'm going to look under H3PO4 and I want moles gone, so I'm going to use that value. I'm going to use the concentration of the H3PO4. So 12.9 moles of H3PO4 for every 1 liter of H3PO4. So what can cancel out? Our moles of H3PO4 and moles of H3PO4 can cancel out. Good, so I'm done with that thing. And then finally, the very last thing, I need to cancel liters of H3PO4. I have kiloliters, which is a form of liters, so let's use it. So let's go 1.00 kiloliters, and I don't really have enough room, but that's totally fine, of H3PO4. So, please focus your attention up on the board here for a second. I want to show you something magical, okay? Magic is about to happen. So, liters of H3PO4 can cancel, but watch this. Liters of H3PO4 and then liters of H3PO4 cancel. But what's left over? Let's take a look at all of the units that I have left over. Liters of NH3 is left over. Great. But also my kilo. That kilo never got canceled with anything. Kilo and kilo could have canceled, but there was no other kilo on the bottom to cancel it. So what am I left with? I'm not going to use any math right now, okay? But my answer is going to be kiloliters of NH3. So kiloliters of NH3. Now we're going to go ahead and put this into our calculator. Sure, no problem. It's not that big of a deal. Every time I do a calculation, you should also be doing a calculation. Using your calculator is a skill that you have to practice, something that you have to get good at. So please take out your calculator and actually perform this with me. So don't care about the 1, but the 2, the 12, and the 1 on the other side I don't really care about. So 2 times 12.9, that's really all I care about on top. And then divided by 14.8. That's it. So I should get 1.7432 blah, 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 but rounded to 3 significant digits, 1.74. So 1.74 kiloliters of ammonia. Okay, so I know that was a long problem. I understand that that took a long time, but hopefully this process makes sense. If you have a solution, you need a volume and a concentration, or you can look for the volume, or you can look for the concentration. In this particular problem, we were looking for the volume, so that's how we did it. We were able to use all this piece of information to try and get the volume of NH3. So what volume of NH3 would be required to do this? 1.74 kiloliters or 1.74 thousand liters of ammonia. So let's try another example. And this one's going to be a little bit quicker. Here, I'll go to a new page. So this is going to be example number 2. In an experiment, ten milliliters of sulfuric acid, so H2SO4, reacts with 15.9 milliliters of 0.150 moles per liter potassium hydroxide. Calculate the concentration of the H2SO4. In an experiment, 10 milliliters of H2SO4 reacts with 15.9 milliliters of 0.150 mole per liter potassium hydroxide, KOH. Calculate the concentration of H2SO4. Again, pause the video if you need a little bit more time, but I'm just I'm going to dive right in here. So is this a stoichiometry problem? Is it giving me 2 different substances, and are they reacting with each other? So like, is it saying you have something of this, how much of this are you going to need, or something like that? So in an experiment, this much of something reacts with this much of something else. Calculate the original concentration of the sulfuric acid. Yep, this is a stoichiometry problem. 2 different substances reacting together, giving me information about one, asking about the other. So we need to write a balanced chemical reaction. Okay, no problem, we can do that. So H2SO4, sulfuric acid, is going to react with potassium hydroxide, KOH. And I was too lazy to write it down, but they're both solutions, so they're both aqueous. Now, it doesn't say what the products are going to be. Like the last reaction, it told us this was the product we're going to make, ammonium hydrogen phosphate. Here, it's kind of up to us. So we take a look at this, and we're saying, okay, compound plus a compound. It looks like at least one of them is ionic, so this looks like a double replacement reaction. So probably the hydrogens and the potassiums are going to swap places. So we're going to get potassium with the sulfate. So we're going to get potassium with the sulfate. And then we're going to get the hydrogen with the hydroxide. So HOH. And this should look kind of familiar to you. We're not totally done yet. Now we got to figure out what the actual formula of potassium sulfate is. Potassium, if you look on your periodic table, is K+, and then sulfate is SO4 2-. So how many potassiums and how many sulfates do we need? Well, we need 2 potassiums. I don't know if you remember this from Science 10 or from earlier in the semester, but any group 1 ionic compound is always going to be soluble. So this K2SO4, it's going to be aqueous. Group 1 things don't make precipitates with kind of one exception. Don't worry about it. And then this thing, HOH, well, what the hell is that thing? That's water, right? So it's going to be a liquid. Okay, let's go ahead and balance this. So we see H2SO4 plus KOH gives you K2SO4. Well, I see 2 Ks, so we need 2 Ks. But there's 2 OHs, so we need 2 OHs. And 2 beginning hydrogens, well, we have 2 beginning hydrogens. So this reaction is balanced now. That really is, getting a balanced reaction really honestly is kind of half the battle when we're talking about stoichiometry. If you're given a balanced chemical reaction, it's way easier just to do the stoichiometry with it. Okay, we got a balanced chemical reaction. Step 1 done. Woo! That's what I'm talking about. Now, we got to place all the pieces of information under who they belong to. So, in an experiment, 10 milliliters of H2SO4. All right, no problem. 10.0 milliliters of this stuff. And then it says reacts with 15.9 milliliters of KOH. So 15.9 milliliters. And it said KOH had a concentration of 0.150 moles per liter. So 0.150 moles per 1 liter. Now what it's asking us is calculate the concentration of the H2SO4. We're doing unit analysis, so I want to write down the units that we're looking for. I could put C question mark for concentration, that'd be great, but the concentration is measured in moles per liter. So I want to know what is the concentration in moles per liter. Good. Let's take a look at it. Like liters and liters can cancel, we can get moles. That's good. This side is good. Liters and liters can cancel, we can get moles. This side is good. Don't worry about the milli. Like I said before, don't worry about the prefixes. They have a way of sorting themselves out. And then how do we convert from one substance to another? Say it with me. We need the molar ratio. No, whatever. That's fine. Okay. Molar ratio. So our molar ratio is going to be 1 mole. It's our unknown. So 1 mole of H2SO4 over 2 moles of potassium hydroxide. By the way, I'm assuming everybody actually said it out loud with me, and if you didn't, I'm super disappointed now. But I wouldn't know, so that means I'm not disappointed. Whatever. So now let's try and do our unit analysis. We have the information for this substance, we have the information for that substance, and we have our molar ratio that converts between the two. So let's do our unit analysis. What are we looking for? We're looking for the moles per liter, concentration in moles per liter of H2SO4. So I got to start with moles of H2SO4 on the top. Now, I don't think we've totally done this yet, where we're looking for a complex unit, something that's made out of more than one unit. But always start with the top unit. Always, always, always. And if you got to finish with the bottom unit, go ahead. That's totally fine. So we got to start with moles of H2SO4. And eventually, we want to cancel everything else, but we also want liters of H2SO4 on the bottom. So we want moles of H2SO4 on the top and liters of H2SO4 on the bottom eventually. Start with the thing on top. That's the easiest way to organize. So look for moles of H2SO4 anywhere. Well, I look under H2SO4. And I don't see anything with moles in it. Okay, shucksy doodles. So we're going to have to look somewhere else. I look at the molar ratio, moles of H2SO4. Yes, that's what I'm talking about. So I'm going to use the molar ratio. 1 mole of H2SO4 for every 2 moles of KOH. We have the unit, moles of H2SO4. We have the unit on top that we're looking for. Now we have to get rid of moles of KOH. So let's look for moles of KOH somewhere. I just used this, so I can't use it anymore. Moles of KOH. Look under KOH and find moles of KOH. So that's the thing that we're going to be using, that concentration. 0.150 moles of KOH over 1 liter of KOH. When we're doing stoichiometry, I really want you to attach the entity, who it belongs to, the identity, to the unit. So if you write down liters, write, well, who does the liters belong to? Liters of KOH. It's liters of this substance. So what does that do? Moles of KOH cancels, moles of KOH cancels. Nice. Okay. Now we need to cancel with liters of KOH. I don't see liters anywhere, but I do see milliliters. So under KOH, we have 15.9 milliliters. Okay, that'll have to do times 15.9 milliliters of KOH. So what happens is the liters of KOH and the liters of KOH, they cancel. So let's just take a step back. I've basically gotten rid of everything. I've got a milli here, sure, whatever. I've got every other unit other than the moles of sulfuric acid. So I want moles of sulfuric acid on top. Great, that's basically what I have. But what do I want on the bottom? I also want liters of sulfuric acid on the bottom. So let's look for liters of sulfuric acid and let's put it on the bottom. So we put it down here. 10.00 milliliters of H2SO4. And kind of a beautiful thing happens. Do we have liters of H2SO4? Yes, we kind of do. We've got liters of H2SO4. And this wonderful thing happens where milli and milli cancel each other out. Boom, done. Just like that. Millis are gone because you got a milli on top and a milli on the bottom, and they cancel each other out. So what are our units that are left? Moles of H2SO4 on top. Great. Moles of H2SO4 on top. And then liters of H2SO4 on the bottom. So that's exactly what we wanted. We wanted mole per liter of H2SO4. Now we just got to put it into our calculator. Okay, sure, whatever, that's totally fine. I go 0.15 times 15.9 on top. 0.15 times 15.9. And then divide by, there's two numbers on the bottom that I care about, the 2 and the 10. So you can divide by 20 if you want, but I'm going to go divided by bracket 2 times 10 end bracket. That should give us 0.11925 moles per liter. So we're going to round that to 0.119 mole per liter H2SO4. So hopefully this wasn't too bad. I have no idea how long the video was. Maybe it was way too long, and I apologize about that. But here was two examples, one where we were looking for the volume and one where we were looking for the concentration. I cannot stress to you enough how you have to have a balanced chemical reaction, put all your pieces of information. Solutions are defined by a volume and a concentration. So you need to have something about a volume and a concentration there. And then you need to have your molar ratio somewhere as well. And then you can perform your unit analysis the way you want to. Okay? Let us know if you have any questions. Let us know if there's anything that we can do to help. Myself, Mr. Zielinski, Mr. Zukowski, Madame Belzile, Mr. Reynolds, we're all available at lunch and flex for you if you have any questions or anything like that. Have fun!